This is an outline of a project that relates to the topic of linear equations and graphs. This project involves using the city map of your hometown. In this case, I'm using Duncan as an example. In Desmos, it is possible to add a drawing, a screenshot of a map. When that happens, the object is placed somewhere in the middle and you can drag it anywhere you want. If you put it in the positive first quadrant, it'll be easier to calculate. The numbers will not be negative. In my case, I put it exactly in the center, like so. So I will end up with some negative numbers, but that also shows the versatility I have in algebra. The main idea is to imitate the streets of the city using lines. So for example, the popular Government Street where our school is located, I pick 2 points that I think belong to the street. For example, this point number 1 and this point number 2. I pick these points based on the coordinates. I can zoom in and check what the coordinates are. And then I want to create a line passing through these 2 points. So we studied how to do those equations, a line passing through 2 points. After some calculations, I end up with a line. Now, if you notice, I have this restriction, which is really optional. But at the same time, in real circumstances, Government Street does not like go all the way straight. So I introduced these restrictions just to limit it between points 1 and 2. This step is optional. Now I want to create another line. For example, I choose Dogwood Avenue, and I also pick 2 points, 1 and 2. They are here in purple. And I want to create an equation of the line passing these 2 points. Again, these restrictions, they are optional. If I were to not have any restrictions, the line would go through Dogwood Avenue. But right now it's limited. My next step is calculate the point of intersection algebraically. So I can navigate and I can prove with Desmos that that's the point of intersection of these 2 lines that model these streets. But I should be able to do it algebraically because that was the point of our learning. Next thing, I want to try and create a couple of other lines perpendicular to the purple line. And these look like a similar intersections that would fit within perpendicular. So these 2 little lines could be perpendicular to Dogwood Avenue. So I pick 1 point here and I create a line passing through that point perpendicular to the purple line, and I do algebraic calculations. I pick another point. Mind you, they're not exactly going through, but the idea is that I'm showing that I'm able to create parallel and perpendicular lines. These blue lines are parallel to each other, and both of the lines are perpendicular to the purple lines. Now, as to the calculations, I should attach how I did the work. This is an example. I'm using the equations that we studied of the equation of a line passing through 2 points, where x1, y1 would be coordinates of point 1, x2, y2 would be coordinates of point 2. We studied all that. So I show how I would calculate the equation of a black line using this formula. And so this is the equation of a black line, exactly as in Desmos. Right here, this black line. And then I show equation of a purple line, how I would calculate that. Purple line is extremely inconvenient. It has a lot of decimals, and then it results with even more decimals. I had to employ Wolfram Alpha for some calculations, just as an example here. But still, I can keep fractions or I can keep decimals. At one point, fractions were a little bit comfortable, so I do have this block circled. it is to my advantage. Okay, then I find the point of intersection and I show this algebraically how it calculates the point of intersection of this black line and this purple line. And I prove that my point of intersection algebraically is exactly the same as the point of intersection found in Desmos. I'm sorry, this point. This point right here with coordinates negative 2.61, negative 2.77, exactly as the calculation. And then the two perpendicular lines, they are the skinny blue lines with like complicated equations here and here. That's why this fraction was convenient earlier. Then I can turn it upside down and put the negative sign so that it's easier to calculate the slope. And B, which is known as y-intercept, results with also a few digits. It might be worthwhile to calculate streets on a positive zone. This is just the way I chose to have the map, but it's obvious that there are a couple of parallel lines here and here, perpendicular, so I did not really need to choose the government street. I could have taken Canada Avenue, for example, and this Beverly Street, and maybe a few like Holmes and Vista. So this project is quite open, and there would never be any repetition because your scale, your map, your hometown, it's quite unique and it shows good knowledge of linear lines and equations.